have that variant B tree. So formally a B tree of order M, this order M is term is important. Okay, so because the M may vary. Okay, a B tree also a general definition. So they are based on this value of M, there may be different kinds of B tree. We'll see later. Okay, so a B tree of order M is an MOA search tree which satisfies the following additional properties. So structurally it will be MOS and search tree, I mean MRE tree with that searching, just like extension of binary search, MOS search will be inbuilt. But there will be some additional restriction. Number one, root is a leaf or has between 2 to m children. So root cannot have, I mean, only one children. Root is leaf, either 0 or it can have 2 to m children. Okay. And all internal nodes must have children between, there will be a lower limit of children and there will be an upper limit of children. Upper limit is same. See, upper limit is m. Since it is an MOS search tree, upper limit of number of children for a node, be it root or be it internal node, will be same. This is m. But the minimum, there is a minimum limit. This is the special thing. Okay. Because what we see that if we don't keep a minimum limit or lower limit for a particular node, that how many children it must have at least, then this tree will become very stray and we lose the balancing or I mean height balancing property. We will have a very large height, I mean almost proportional to n, that we don't want. So that is the main reason why we include this thing. And in B tree, it is this particular value is m by 2 floor, it is set. Whatever may be the value of m, that will be the maximum number of children that is possible, and m by 2 floor will be the minimum number of children that an internal node must have. Okay, and this is another important property, that all leaves are at the same depth. And this particular property actually it acts as a constant, that all leaves must be at the same depth. And this property will ensure that your tree will be properly balanced. When you are forcing that all leaves are at the same depth, that means you are actually allowing only fully filled trees. Are you getting my point? Consider a binary tree. If you ensure that all leaves are at the same depth, that means you are only allowing full binary trees. Understood? So, and in that case, it is obviously it is a very restrictive thing, but at the same time, you are ensuring that it for binary tree, it will be always attain log n bound. Similarly, for this MOS search tree or for this B tree, this property, it's a very restrictive constant. It will be very difficult to maintain, but we have to maintain so that automatically the height balancing is achieved. We'll see when we actually illustrate insertion, deletion or construction of B tree through examples. We'll see that how this particular property helps us to make this tree self-balancing in nature. Okay, so this definition is clear, everybody? Hello, just please respond, since this is a very small class. I want to
Yes,
make it interactive. Okay, so this definition,
Yes, yes, sir.
Yes, sir.
Yes, sir.
is there any objection? Hello?
No, sir.
Hmm?
No, sir. No problem.
Okay. Okay, so basically there are many B tree variants of B tree. I will be discussing this 2, 3, 4 tree mainly to illustrate the different kinds of operation on B tree. Okay, so this, see this, the minimum, the aim is the order, and that is only unique property of a B tree that you should know. But this, when this minimum, this lower uh, bound on the number of children of a node, that is m by 2 floor, is also called minimum degree of the B tree. So this is not that much important, because this order is important. If you know the order, so for a 2, 3, 4 tree or 2, 4 tree, order is 4. That means maximum number of children a node can have is 4, and minimum number of children a node should have, any internal node should have 4 by 2, 4 by 2 ceiling, which is 2. So this 2, 4 tree or 2, 3, 4 tree is, the name suggests that any node can have either 2 or 3 or 4 children, or there is another convention which is written as 2/4 tree. That means the minimum possible and maximum possible is mentioned. Okay, or you can say B tree of order 4. So same tree you can mention in 3 different ways. Okay, all of them are representing the same thing: 2, 3, 4 tree, or 2-4 tree, or B tree of order 4. Same thing. Okay, so 2, 3 tree is another kind of B tree which we will not discuss. And then maybe actually in practice the order will be much higher than this 3, 4. Okay, but it is very difficult to illustrate the operations using that much large tree. That's why we are only considering 2, 3, 4 tree for illustration. But actually in practice databases, the order will be larger than 4. Now you might find a very related convention, I mean name of some very closely related trees appear in some literature, that is B plus tree or B star tree. Okay, so what is the difference between B tree and B plus tree? Conceptually they are same, but only difference is that in practical implementation, what happens in B plus tree, uh, the actual data containing nodes, those are only appeared in leaves. That means all the nodes which appear, I mean non-leaf nodes, they only contain key elements. They don't contain any useful data for that node. All nodes that are contain that contains useful data, okay, they are kept in the leaf node, so that the entire tree apart from that leaf node are kept in the main memory, and any path from root to leaf can be traversed by traversing through n-1 nodes which are already available in the main memory. Because see, this traversing, searching, everything is done on the basis of key element only. Now the last lap, which is from the just parent of a leaf node to the parent node, will be a disk access. So basically the non-leaf portion of the tree actually is used to identify the appropriate leaf during searching where the data could be found, and then the actual data is accessed by making only a single disk access. This is the whole idea. Okay, it is expected that if this is possible, then it will be very good, because every time I can access any node by single disk access. In order to do that, many people used to keep the organization, practical organization of a B tree like this, that all non-leaf nodes actually they are they are kept for only facilitating the searching process or during insertion or deletion to identify the appropriate leaf node. Okay, so they don't contain any useful data. All useful data are stored in the leaf nodes, and so that the entire thing, actual database, is stored in the disk, and the remaining part which facilitates the searching or traversing part is stored in the main memory, uh, having only key elements, that is only required thing. Okay, so that is the difference. B tree is kind of general definition. You can store. I mean, in case of your practical organization, you can store all the required data element along with the key element at every node, as the normal practice, which is done for non B tree type of trees, which we have already discussed, like binary search trees, AVL trees, whatever. But in disk-based data structure, this is a good idea for practical implementation, where you can store only key elements in non-leaf nodes and all the actual data in the leaf nodes, and that variant is called B plus tree. Understood? Okay, similarly, B star tree is just, I mean, from B tree definition, it is clear that the minimum number of children of a node is m by 2 and maximum is m. So we are forcing, the definition of B tree is forcing that every node must be at least roughly half filled. You cannot have a node which is less than half filled, because full filled means there are m minus 1 elements, so that it can have m children. Now half filled means there are m by 2 minus 1 elements, such that it can have m by 2 children. But no node in internal node of a B tree can have less than m by 2 minus 1 elements. That is not allowed. So roughly we can see that B tree, I mean every node of a B tree must be half filled. Okay. Now B star tree says that each internal node is required to be at least 2/3 filled, so that it actually restricts the minimum number of elements should be larger than B tree, so that the growth of height is more slow than B tree. Okay, this is just difference, B star tree.
Sir, sir, 2 by 3 full means it should have 2m by 3 children, right?
Yes, 2m by 3 children, roughly. That floor or ceiling thing you have to adjust. Okay. So these are just variant. I mean, only B tree conceptually thing is that there should be a lower bound and there should be an upper bound. If there is no lower bound, as we have seen in case of binary tree, it can go skewed towards left and right, and then it can lose the advantage of log n bound. It may grow up to order of n, and in order to prevent that, this lower bound is attached. Okay, and if you want more I mean more breadth-wise extension, then you can have this 2 by 3 full. But B tree, it just m by 2 ceiling, 2m. Okay. Now the main important thing, as you have already, probably you have already understood that from this discussion, that choosing the appropriate order of B tree will be very crucial, isn't it? What should be the value of m in case of a B tree? I am taking B tree of order m. Now, what will be the optimum value for m? What should I take? Whether it is 4 or 50 or 500, what? Okay. The answer is that there is no straightforward optimum number. Okay. So it depends on application. But how do you actually choose? What are the factors you need to consider while choosing the particular value for the order? Any idea? What factors you should consider while choosing the order for an B-tree?
Sir, the amount of data.
Amount of data, fine. Larger the amount of data, you will choose larger M. Any other thing? I have already mentioned those things, maybe in a different context, but just try to apply your common sense. How do you fix? See, ideally, I can say, vaguely, I can say that M should not be very less, because if I take M equal to 2, what does that matter? Mean? It will become binary tree, as good as a binary search tree, M equal to 2, isn't it?
Yes.
Now, again, I cannot recommend that you should take, is there any, so lower bound is understood that I should not have M as less as 2 or very close to 2, 3, 4, like that. Okay, I should choose the order big enough. But the next question comes whether I can take any value, which is like if I have 1 million data, should I go for 1 million value of M to be a 1 million, or at least half million, or 0.2 million?
No, sir.
Why?
That
Obviously,
will be
that
a
should not be
that
the
will be a
case.
linear search.
Huh?
That will be a linear
Exactly.
search.
There is a trade-off. Once I am increasing the value of M, that means number of nodes will be less, height will be less, but within a node, number of elements will be huge. Because if M is 1 million, that means a node can have at most 1 million children. That means the node has, in that case, the node has to accommodate 1 million minus one number of elements in it. Now, in order to find the appropriate branch, which I need to follow while traversing or searching, I need to perform a search, and that whatever search I employ, binary search or linear search, when it is the it is acting like a large array of 1 million size, so that searching time will be very high. Maybe the number of hops which I had to make from root to leaf will be less, but within each hop, in order to choose the next hop, I have to compute many, I have to perform many computations like comparison. Okay, so the gain on the one hand I am getting will be lost in this manner. Clear? So this trade-off must be addressed. So it should not be as large as now. Now we are in a very vague position. One point we are telling that it should not be as less as 2 or very close to 2. It should be large enough from 2, and at the same time we are telling that it should not be as large as the uh, size of the data. It should be very less than that. then what will guide us? Who will actually help us to actually solve this trade-off? Any idea?
So if we can fix the number of allowable children for every particular node.
No, see, number of allowable children is fixed by the value of m. Because for any m, maximum is m, minimum is m by 2. So everything depends on m. So now we are actually coming, what should be our desirable value of m? And for that we have seen the trade-off is that m should be large enough than 2 and m should be enough less than this 1 million or whatever, some big number. Now what should be desirable value? That is the question. So how do we address this trade-off? See, I have told that in case of practical implementation, disk access is very important. Okay. Now, as I mentioned, every disk access is costly in terms of time, but at the same time, depending on a particular machine, the amount of data I can fetch per disk access is fixed, and that is called block size. The block size may vary from machine to machine, but for a typical machine, the block size will be constant. Now, if I choose this may be a guideline for me what should be my maximum possible size of a node, because if I have fixed a large m such that the number of elements that a node can contain at most is cannot be fit inside a block, then for fetching a single node, I need to perform multiple disk access, which will be more costly. So I would always try to fix my m in such a way that the number of elements a node can at most have must fit in a block size, so that only one disk access is sufficient to retrieve or fetch that entire node. Understood? Sounds logical? Students, are you getting my point?
Yes, sir.
Yes, sir. Yes, sir.
So apart from this cost involved in sequential or binary search that will be involved in choosing a particular branch per node, this practical thing we need to keep in mind, that I should not fix a large value for m such that maximum possible data within a node becomes more than a block size. Okay. But obviously the block size may be very large, just like 8 KB. Now always it is not a good idea that I will choose the value of m so large that a node, the maximum number of data, that number of elements will be proportional to 8 KB, because that also require number of keys, see, 1000. Okay, if 8 KB block size is allowed and 4 byte is spent for integer keys, so maximum number of elements is 1000. Now you may not allow 1000 keys per node also, because searching 1000 keys is also costly. If it is possible to keep 500, that is also okay. Okay, but you should not exceed this 1000 anyway. When your block size is 8 KB, okay, you should not exceed 1000 because that will insist more than one disk access per node, okay, which is very much undesirable. Anyway, programmers have done lots of empirical experiment on some benchmark setup to understand what will be the optimum value for M. There is some result which shows that the curve looks like this one. When you increase the value of M, so when the value of M starts increase from 2 to about 40, 45, the search time reduces drastically, but it then becomes saturated up to a value of about 300 to 400, and then increasing further becomes increasing further, the searching time grows exponentially. So this is not, I mean, this is just a guideline. This is not true for all programming environment and all setup. Okay, so this was done with a benchmark setup with some specific values for this block size and the other parameters like processor, memory capacity, everything. But the good thing is that this structure of this graph will remain almost same. This actual values may differ in your case. This 50 here, this transition occurs at about 50 and this transition occurs at about 400. In your case, this may not be 50, it may be 60 or maybe 100, it may be 30. Here it may be 200, 500 or 700, but the structure will remain same, as you have already understood the basic philosophy behind this uh, searching time and relationship between aim and searching time. Okay. So anyway, let us now move into the actual uh, illustration of operations, insertion, deletion, construction of B tree. And as I mentioned, I will illustrate everything on this 2-4 tree or 2-3-4 tree. Though it is very impractical, you will not find 2-4 tree in practice as a B tree because this order is very small. But in order to understand these operations, we should accept this. Okay. So this is just a definition. The same B tree definition here, just aim is fixed. Okay, so 2-4 tree is an MOA search tree which satisfied the following additional properties. Each internal node has at most 4 children because M, the order is 4. That is either 2, 3 or 4 children. That's why it is sometimes written as 2-3-4 children.
Excuse me,
Okay.
sir.
Yes.
Sir, is 2-3-4 tree same as quad tree? Because quad means 4, I think. I have heard something like quadry is there.
Maybe I didn't find this term. I have to check.
Okay,
Maybe because quad means 4. See, again, binary, it may be, I mean, 4 array tree, maybe. That is quad tree. But B tree is not just 4 array tree. Just like binary search tree, AVL trees are not only binary tree. Okay, so
yes,
quad,
sir.
maybe I'll check, but it seems that uh, quad tree is just a 4 array tree.
Okay, sir.
But yes, 2-4 tree is additional, I mean, apart from just a 4-array tree, it has some additional properties which I am discussing. Okay.
Okay, sir.
So every node can have at most 3 elements in 2, 4 tree, because number of children, maximum number of children is 4. So maximum number of elements will be 3. Similarly, minimum number of children in any internal node will be m by 2 ceiling, that means 2. So minimum number of elements in a node will be 1. Okay. And all leaves are at the same level. As I have said, this property will be the constant which will help us to make any insertion, deletion, or any updation on the tree to be self-balanced. Okay, so this is an example of a 2-4 tree. Just check. Mind it should be a 4-way search tree first. Okay, so searching, that 4-way searching is a natural extension of binary search. So these key elements, the values of key elements, that less than, greater than, those things you have to maintain first. Then whenever you are considering B tree, you first must ensure that structurally it is all leaves should be at the same level, structurally that maximum number of children, minimum number of children. But you should not forget about that MOA search or that search mechanism. So this position of these key values is very important. I cannot have 10 here, right of 86. Okay, so this often we forget. Whenever we get some new additional properties, we forget the actual property based on top of which we are considering the additional properties. Okay, so this MOA search mechanism. So if you take an in-order traversal of this tree, all the key elements should appear in ascending order. You can check. Okay, so no node is having more than 3 elements or more than 4 children. This is the maximum fully filled nodes. This particular node is fully filled. This is also fully filled, which is a leaf. But all other, this is half filled, we can say. This is also half filled. And this is in between, 2/3 filled, you can say. Okay, so this type of thing is possible. So all the nodes are satisfying the properties and the entire tree is satisfying the properties of a B tree of order 4. So this is an example. Now, what will be the maximum and minimum height of B tree of order 4? It is very interesting that minimum height of 2-4 tree will be half of that of a binary, balanced binary tree. It's half of log n, because it's a MOA tree, fully balanced MOA tree where m is 4. So log n base m, which is 4, and log n base 4 is basically nothing but half of log n base 2. Okay, similarly maximum log n base 2. Okay, so it's a see, structure will remain same here. Why this change maximum minimum depends on the height, same height. We are representing how many different elements we can accommodate. This is very interesting to note that like binary tree, the actual structure will not vary, because here it will be structurally always a full tree. But why this actually varies? Because number of elements that can be accommodated when it is all nodes are half filled will be different than when all nodes are fully filled. In that way, this varies. Okay. So basically, same height, number of elements will be different, and that's why we are taking, actually height will not be different in that sense. Okay. For nodes, if you consider nodes, it will not vary depending on the number of elements. So this is the distinction you need to understand. In case of binary tree, since every node can have at most one element, so nodes and elements were can be used interchangeably. But in case of MOA search tree, in general MRE tree, MOA search tree or B tree, this number of elements and number of nodes, they are different. Okay. So don't get confused with this term. Try to understand that. Okay. Anyway, let us come to the insertion. So this is the process. You just go through this once. I will illustrate. So basically what happens, we insert, while inserting a particular element, obviously insertion will take place at a leaf as usual, and the leaf, a single insertion may exceed the capacity of that leaf, because we know depending on this value of m, maximum capacity of a node is fixed to m minus 1. Okay, for this 2 4 tree it is 3. Now when it exceeds, that means overflow occurs, you cannot keep that thing, because that will violate the property of B tree. So what you have to do, you have to split the node, split that leaf node into half. Like in the middle element, you have to choose the middle element and move that middle element upward and place it in the parent of that node. Now in doing so, when you are moving a node, element from lower part to the parent, then the capacity of the parent may also exceed. Then you may have to split that parent also and recursively do that thing. And in the worst case, you might have to go up to the root, and that root's capacity may also exceed, and you have to split the root. And in that case, the height of the tree may get increased by 1. So every time you don't need to go up to the root. In some cases, in the worst case, you need to go to that. But the idea is, whenever a single insertion makes that particular leaf node overflown, you just split it and move the middle element up, and just check whether that movement disturbs the capacity of that parent also. If so, do the same thing, and it may go up to the root, or stop as soon as you find a parent node which is whose capacity is still to be filled. Then you stop there, unless in the worst case you might have to go up to the root and split the root, and in that case height will grow by 1. So
Sir,
here, yes,
sir, in this insertion, how we will know that the node, that the value we are inserting is key or data?
yes,
The value we are
repeat.
inserting is always a
Hmm.
key,
Hmm.
or it can be key or data, anything.
No, no, no. See, everything will be depending on implementation. Okay. So if you have chosen that you are implementing a B tree, not B plus tree, okay, then you have to move everything. Okay. But any operation will be guided by only key element. When I am talking about moving a key element, that means if you are not implementing B plus tree, you have to move the entire node with that key element with you. That's the implementation issue. Okay. Just like you have done in case of AVL tree, deletion, insertion. Insertion means we have shown only key element, but actually the node containing the entire data gets moved. when we replace with in order predecessor, that means in order predecessor node, entirely node gets replaced. Okay, so it is not that only key element. Okay, but if you are implementing b plus tree, then it will be only uh, that key element, but obviously you need to keep track of that. Okay, so that in the lower leaf node it reflects some changes. Okay, understood?
Yes, sir.
Okay, so let me illustrate this mechanism by a simple example, and in the same time I will also illustrate the construction, because as we have seen in our experiences of discussion of other data structures, that if we start from an empty tree, it will, and inserting key elements one by one, it is also illustrating insertion as well as the construction. So let me take this example. So starting from an empty tree, we have to insert these elements. Okay, obviously nodes with this element, we will consider this element representative elements as the representatives of the nodes to form a 2-4 tree. Okay, so first 60. So this will be the single node having only one key element 60, that is allowed, because for 2-4 tree the minimum possible uh, and this root is a leaf. Okay, and has m 2 to m children, so root is a leaf, this condition is getting satisfied. Then 30, still the capacity is not, because maximum number of element is 3 for 2-4 tree. So when I insert 30 here, the number of elements is 2, so it's okay. Then 10 also I can insert, no problem. Now I have exploited the maximum capacity of this leaf node. Now next 20, when I insert, obviously see within the node I am keeping the elements in sorted order, as that is the desired property of MOS search tree, so that I can facilitate the searching with binary search and facilitate that left to right associativity of branch selection. Okay, so next 20, when my 20 enters, this node becomes overflow, because a node cannot have 4 elements for a 2-4 tree, because the order is 4. So maximum number of children is 4. So maximum number of elements is 3. So what I'll do, I have to split them and move the middle element up. Now in this particular case, when m equal to 4, middle element I can consider either this one or this one, any one. But I have to be consistent. Remind that if I choose that the right portion, I mean there is two middle element, I am choosing the right one. So in every case I have to choose the right one. If I choose the left one, in every case in the next other cases also I have to choose the left one. So anyway, without loss of generality, let us, I am considering this as a middle element 30. So I'll split and move up the middle element. So see, so far the height of the tree was 0, because the root was the leaf element. Now when I'm moving this 30 up, that means this will become, tree will become like this. 30 will become root, and this 10, 20, this node will become left child, and this will become right child. So this root node is now containing only one element. So it has 2 children, and these are leaf. Okay, try to understand. This will be the thing. So now see, this is a very interesting change here we have observed, that the increase of the height is going, I mean, is occurring upwards. In other cases, so far, insertion took place at the leaf node, and in case of binary search tree or whatever we have seen, we insert at the end and height grows towards, I mean, lowest level. But here it is as if growing towards upward direction. This is very interesting, and this is actually necessary in order to maintain this property that all leaves are at the same depth. That's why this is the only possibility. You cannot have like this 10, 20, 30 and 60. You cannot place 60 here and can have 10, 20 like this. Then one leaf will be here and other leaf will be somewhere else. Not that is not possible. Okay, so every time you have to split at the leaf, and if height gets increased, be it will be placed in the upward direction so that all leaves remains at the same depth. Okay, so these four elements so far we have inserted. Next 50, what I have to do? 50 I will compare with the root. Since 50 is larger than 30, so I have to choose the right branch. Then this will be the appropriate leaf which is having capacity, so 50 will be inserted here. Okay, now 40 is also greater than 30, so I choose the right path and it will be inserted here. Now 70, same thing, 70 should be inserted here, but that will cause this particular node to overflow, and as usual I will split and move up. Now which element will be moved up?
60.
Yes, because I have to follow the same convention, either 50 or 60, but I have considered the right one as the middle element for tie breaking. So 60 will be moved up, and see the change of pointers. This is very important. 60 will be moved up in the root, and now root now is having 3 children. Earlier it had 2 children. Now it is having 3 children. And this pointer manipulation is very important, because when you will implement using or program, write program to implement this thing, you have to actually do this pointer manipulation. So this 30 to this node was parent-child relationship. This pointer was pointing towards this, but now you have to have 2 pointers coming from this node like this. This manipulation pictorially it is very easy to show, but in order to implement it, it will be very difficult. Okay, so try to understand this pictorial representation very properly, that what should be your strategy of manipulating pointers, then go and implement it. Okay, now next 80 will be as usual. It will follow the rightmost branch and will be placed here. 15 is less than 30, so leftmost branch will be considered, and it will be inserted in between 10 and 20, since we need to keep them in ascending order. Then 90 will be like this. 99 again will lead to a splitting. Okay, so 90 will move up like this, and here again there will be another pointer adjustment we need to consider. And now see, the root has become fully filled. This node is fully filled. Now 35 is in between 30 and 60, so it will be inserted here. Okay, so the insertion strategy is clear.
Yes, sir.
So basically we are actually performing 2 pass. Okay, and just we used to, first pass is very common. I mean, that is the natural extension of the insertion of binary search tree. We are just performing an MOS search to locate the appropriate leaf where I need to insert the element. That we used to do in case of binary search tree also, any kind of binary search tree. In order to insert, we start from the root, perform comparison. Based on that, we choose left or right branch and reach at a particular leaf from where I don't need to go anywhere. And then the new node is inserted as a left or right child of that leaf. Here, same thing. I am moving downward, starting from the root to locate the exact leaf where I need to insert. There is no question of inserting the new node as a left child or right child or any child of a leaf node. I have to insert it inside the leaf. Now, if that insertion exceeds the capacity of that node, leaf node, then what I have to do? I have to split and move up the middle element. And this is a upward pass. This is an extra pass which I had to make in some occasional cases, isn't it? This upward pass is an occasional step, and this is the additional step. And in the worst case, I might have to perform this every time. I mean, these two pass. Okay, and these two pass, the length of the second pass may be different. Sometimes I may have to just go one node up the leaf node. Sometimes I may go up to the root itself and split the root. Okay, so this is the summary of the insertion strategy we have illustrated so far. Clear? Any question?
Sir, what? How we search for appropriate leaf?
That's the MOS search. Just like binary search is employed to search the appropriate leaf, here we have employed MOS search starting from the root. I have explained, na? Suppose this one, I have to insert 80. So what I will do? I will come to the root. I will compare, okay, 30 and 80. 80 is greater than 30. So I have to move here. Okay, 60 and 80. 80 is greater than 60. Okay, so I am following this extreme right path. Same thing.
Okay, sir.
Obviously this is a very small tree. If there were some other thing, I have to, so every node I have to perform a linear search or binary search to find out the appropriate branch to go down further. Just natural extension of binary search. This is called MOS search. Okay,
Okay, sir.
got it?
Yes, sir.
Now, there is another alternative of this two pass insertion. Is it possible to have a single pass insertion also? We don't need to make this downward pass and then upward pass like that. Only downward pass we can insert. Okay, this is called single pass insertion. The strategy is very same, but here what we are doing in the first kind of insertion, in two pass insertions, what we are doing, we are inserting first in the leaf and then we are checking whether that insertion is violating the capacity of the leaf, and then we are adjusting accordingly. Okay, this is the reactive strategy. That means whenever it is hampering the capacity, we are taking the action. Now that's why we have to, after finishing the downward pass, we might have to move upwards sometimes. Okay, but in case of single pass insertion, what happens during the downward pass, proactively we keep the arrangement in such a way that no nodes in the path which I am following from root to leaf while figuring out the appropriate leaf for insertion, I am ensuring that no node in the path is already having maximum capacity. So if there is a node already having maximum capacity, I will proactively split it when coming down. Split it and adjust such that when I reach at the leaf, the path, because see, the path I am following for downward pass, the same path I had to follow for upward pass, for adjusting the capacity. But if I am ensuring that that path, I am already taking proactive action to make sure that no node in that path is having maximum capacity. All nodes are having at least less than one particular element it can accommodate. Then I would never require that upward pass again. Are you getting my point? Understood my point?
Yes, sir.
So let me illustrate the same example with single pass insertion. Let's see how it's changed. So 60, 30, 10, it will be same as it is. Okay, I'm just moving fast. Now what about 20? See, this is also, since this is the beginning, it will be, you may not actually identify the difference, but still, so whenever we are starting 20, see, now this is all completely filled, so I will split fast. See, in double pass insertion, I had inserted that and then split and then do the stuff. But here, what I am doing, just whenever I am seeing that I have to insert a new key, forgetting about anything, I am just checking whether this node is already completely filled or not. So since it is filled, I'll start splitting it first. This proactive action. Okay. Then I will insert 20. So after insertion, I don't need to do anything. See, up to this step, the end result is same, but actually the order of operations is different. Okay, that will be more clear when we'll move further. Are you getting my point? I mean, this insertion of 20, at the end, the result become almost same, but the strategically the operations, in case of earlier strategy, we had inserted 20, then we had moved 30 up. So 10, 30 becomes the left child of 30 and 60 becomes right child. But here, before actually inserting 20, I am splitting 30, 10, 30, 60 like this. And then I am coming down to this and inserting. So I would never require to go again upwards. Okay. Similarly, 50, see 50 is greater than 30, so I will move this one, and also I have checked that this root node is already having capacity. Okay, so I will not do anything, I will just insert 50 here. 40, again
Sir,
40 is
in
greater,
case of
huh?
50, sir, in case of 50, we can insert 50 in the root node itself because it is having space there. The
No, no,
capacity.
no. The insertion will always take place at the leaf node itself.
Okay.
If it is having space, that means I can go ahead. Here the only thing is that if it is already having 3 element, then I have to split it. That's all. But insertion will always take place in both the cases. Insertion will always take place at the leaf node itself. Okay. You cannot insert in any intermediate node. Actual insertion. Understood?
Sir, in this way, the root node will always have one node.
No, no, no. So how it will be, see, as it will grow, the one child of the root node may become completely filled.
Then we will split it again.
Yes, whenever you are splitting a child node, automatically splitting means you will move the middle element up. So the capacity of this node will increase in that
Then
way. You
we
see, you
merge into
just
the root,
see,
right?
yes, you just see this example, you will get to know all the possibilities. Okay, it will not remain with single nodes, never. Are you getting my point?
Yes, sir.
So 50 insert 50, 40, 40 will again follow this path, and these two nodes are all already having less than the maximum possible capacity, so I'll just insert it. Now let's see 70. 70, this is okay. 70 also says that you should follow this right branch, and this root node is still having capacity, but when it comes down here, it sees that this left node is already having the maximum possible capacity. So before it inserts 70, it has to split it. And see, this splitting actually increase the number of elements in the root node indirectly. Splitting means what? When you are splitting, you are also moving the middle element up. Are you getting my point?
Yes, sir.
Yes. So now this completes, then 70 will get insert here. So see, in single pass insertion, actual insertion takes place at the end. Okay. In double pass insertion, insertion takes place first, actual insertion, then if needed, splitting is done. But here, insertion always takes place after checking whether I had to split or not proactively. If needed, I will split, then I will insert. The splitting may be optional depending on the requirement, but it will always come before insertion. That's the point. That's the difference between double pass insertion and single pass insertion. Okay, so these three steps complete the insertion of 70. Next 80. See, now 80, I am comparing 80 is greater than 30, so I will move up, move right. 80 is greater than 50, I will move right. So this rightmost link has to be followed, and also I check the root node is still having one less than the maximum possible capacity, so I don't need to split it. I will come here and I see it is also, this particular leaf node is also having one less element than the maximum possible capacity, so I will safely insert 80. Okay, so there is no requirement of split. Similarly 15 is less than 30. Okay, so I will come here, and since both root and this node is still having capacity, so I will insert 15 here. Now what about 90? Tell me, what will be the step of insertion of 90?
Sir, we will go to the right child and we will split it, and then we will
Yes.
insert.
Go to the, so 90 means I have to follow this path, and this path root node is still having enough capacity, but this leaf node is not having enough capacity. So I have to first split the leaf, this leaf split, and then, and splitting takes, splitting requires the pointer adjustment. This is very important. Okay, and then I will insert 90 on right of 80. Okay. Now see, this is most desirable, I mean those desirable case, the 99. Now whenever I am thinking now anything, any value I now want to insert has to pass through root. See, root to leaf path will always include root. So be it 90, be it 80, be it 70, be it 10, 20, any value. When I have to insert next element, I had to split the root, because I have seen that root is now having its maximum capacity. In single pass insertion, I have to proactively first split the root before trying to insert anything. Okay, this is the difference. See, I'll split first, so that now I can start, I can ensure the path 50, 70 in this node. This path will have to be followed while inserting 90. Now all the nodes along that path is now having enough capacity. So this proactive action is made first, and then 99 is inserted here. Just try to concentrate on this insertion. Insertion of 99. It starts by exploring the root node. Root node is completely filled. So before doing anything, split the root node like this. And you see in this process, the height of the tree gets increased by 1. Doesn't matter. Now you start moving down 70. This node 70 is having enough capacity, no need to split. Now since 99 is greater than 70, you follow this, and since this node is also having enough capacity, you don't need to do anything. No splitting is required for the only insertion. Okay, understood? Understood?
Yes, sir.
Okay. The last one, 35. 35 is less than 50, so I will follow this node, and see root is only having only one element, so enough capacity is there. Then 30, this node contains only 30 element 30, so this is also having enough capacity. And then see 35 is greater than 30, so I have to follow this path, and this node is also having enough capacity, so I will just insert 35 here, left of 40. But be it 28, what would happen? For 28, I had to follow this path, and since this path, this leaf node is having enough already capacity exhausted, so I had to first split it, then insert 35. But in this case, the insertion will be very trivial. Now, another thing you might observe that in the same set of examples, the tree you have got may be different, which we have got in double pass insertion and the single pass insertion. The two tree may be different. You can just check. This was the tree which we had got in double pass insertion. Okay, and this is the tree which we had got after single pass insertion. So the height of this tree is one more than that earlier one. It may happen because we are proactively splitting. See, in double pass insertion, although we have to make occasional upward pass, but we are actually reacting only if our capacity is really exceeded. Capacity of a node gets really exceeded. That's why the height will be the minimum possible height in double pass insertion. But in single pass insertion, we are actually proactively splitting. It may so happen that we are splitting a node which was not required. We are proactively splitting to ensure that we would never require a upward pass. And that's why the height of this resultant tree is maybe sometimes one greater than the height that we may get in double pass insertion. That is one difference. Okay, so there is trade-off in double pass insertion. We have to make a double pass that is also costly. We have to sometimes make upward pass that is costly, but it is guaranteed that we will get the most compact tree in double pass insertion. Whereas in single pass insertion, we might be having at least one more height in some cases. It is not always, since we are doing this proactive splitting, we may lose in terms of height. Okay, but obviously we'll make sure that the only one downward pass will be sufficient. So do you understand the difference between this double pass insertion and single pass insertion? Okay. connection. Is it okay, students?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So I am not going to discuss the deletion part today because we have just I am showing one example. I am giving one example. You try it out right now. I am skipping the deletion part. I will discuss this tomorrow or day after tomorrow. Now, what I am saying, this one, this is a. You just try to solve this question. Construct a B tree of order 5. So this is not a 2 4 tree. This is a B tree of order 5. So 5 by 2, that means you may call it 3 5 tree. Okay. So maximum number of children is 5 here. And so maximum number of elements per node is 4. And minimum number of children is 3. So minimum number of elements in a node is 2. In that case, you have to insert this for keys. Okay. You just follow any single pass, double pass, whatever you have understood. You just carry it out. Just do it in your exercise book. Try to do it. Remember, this is B tree of order 5. Okay. So the number of keys may look like very large, but per node, the number of keys will be more than the 2 4 tree. It will be 4. Maximum 4, minimum 2 number of key elements. So it will not be that much big.
Sir, can you please show the elements once?
It is not shown. Oh, whenever I change the thing, it okay. Okay.
Yes, sir, done.
Done.
Sir.
Okay, check it whether. So the first four items will go into the root 1, 12, 8, 2, because maximum 4 is allowed. So I am skipping some steps. It will be 1, then 1 and 12, then 1, 8, 12, then 1, 2, 8, 12. Okay. Now the root or leaf, whatever you call it, it is having the maximum possible thing. So the next insertion will split the root. I mean, if you follow the two pass insertion, you first insert 25 and then split it. So 8 will go up. This will be the thing after 5 elements gets inserted up to 25. Then 5 is less than 8 and it will appear on right side of 2. Oh, this is 6. Where is this 6? Okay, this 5 and 6. This is 6 here. So I have to change this one. 5. This 5 and 6 you consider the same elements. Okay, this. Then 14 as usual will come here. 28 will also come here on the right side, since the maximum possible elements is 4. Next 17. 17, see, 17 has to inserted in the middle of this right leaf, but that will exceed. So 17 will be again the middle element of that. So 17 has to go up and it will be splitted like this. Okay. Then 7 will come down here, right of the left leaf. 52 also will come on the right of the right leaf. 16 will move here, 48 will move here. Okay. The next 68. 68 will be following this, and so 48 has to move up. Okay. Then 3 will come here. 26 will come here. 29 also come here. 53 will go there. 55 will go there. So up to this. Now 45. 45 has to come here, but it will be already filled. So 28 has to go up. It will be splitted. This 1, 2, 3, fourth node will get split. Okay. And then the root has to again go and split. This is a step jump is there because when 28 move here, then 17 has to go up. Okay. So there will be two split. So this is the final tree for 2-pass insertion. Have you got it? All of you?
Yes, sir.
This is the final tree. Single pass insertion tree may be different, but for double pass it is there. Okay. So before I stop, I am giving another exercise. You just take this one. This is your assignment. This will be simple. Use single pass insertion and double pass both. You can try. You can check. So this tree is given. Now you have to insert BQLF. So here you see these key values are not numbers. These are letters, and you can just for comparison you can just use the alphabetical order. I mean, okay. You just take it down because I will send the slides, but it may take a few minutes, a few times, I mean, to adjust the slides. I'll send the slides to Abhishek, and Abhishek, you should circulate it, okay? I'll not upload these slides in Moodle
Okay,
because
sir.
this is not the formal course material. So those who are attending, you can have these slides, no problem. You can share it with other friends also, no problem, but I will not going to post it in the Moodle platform. I will send it to you, Abhishek. You
Okay, sir.
circulate on your groups, no problem. Okay. Okay, so I'll be stopping here today. And maybe if I think your classes are starting by Monday, na? From 11.
Yes, sir.
Did you get the class routine?
No, sir.
Okay, it will be circulated. So I just let me check. You
Sir,
have drawn a tree,
civil department got, sir. We didn't get it yet.
but I'm checking. I mean, I have got a preliminary draft of that, which will be sent to you maybe after the approval of HOD. Okay,
Okay.
I'm telling you that which half you do have. Uh, in your classes, I mean, your classes will be held on first half or second half.
Sir, second half.
Oh, then we have to make a different plan, na? I was thinking of taking the class in this slot only. This slot is very comfortable for me.
Sir, is it like same for everyone? Because civil is having in second half, sir. That's why I said second half.
I think so because for every batch it is same. I think so. Let me check it. Let me check it. I'm stopping my presentation. Then I'm checking whatever I have got.